Hey everyone, and welcome to this explainer. I am absolutely thrilled you're hanging out with us today because we're going to uncover a hidden mathematical rhythm that is constantly playing right in front of our eyes. Have you ever felt like some things in life just naturally fall into a perfect, predictable order? Well, actually, that's not just a coincidence. That is the absolute magic of mathematical patterns. Okay, think about this for just a second. What do the perfectly structured rings of a honeycomb, the soulful harmonies of a mouth organ, and the ticking fare on your taximeter have in common? On the surface, they seem completely unrelated, right? But honestly, look at this list. Underneath all their real-world applications, every single one of these relies on the exact same mathematical engine. They all operate on this brilliant, predictable rhythm where things grow or shrink by the exact same amount every single time. It's a concept that not only shapes our physical world, but is basically the cornerstone of your grade 10 math curriculum. So here's our game plan for today. We'll start with patterns in our world, move into decoding arithmetic progressions, then finding the nth term, summing it all up, and finally, real-world math mastery. All right, let's just dive right in. Kicking things off with Section 1, Patterns in Our World, looking at nature and numbers. So picture how bees build their homes. They start with just a single central cell, but from there, they build these expanding rings. And the first ring always has 6 cells, the next has 12, the next has 18, and then 24. Look at that pattern. The number of cells is increasing by exactly 6 every single time. And you know what? We do this kind of thing too. Imagine you drop 50 rupees into a piggy bank on day 1, and every day after that, you decide to deposit exactly 15 rupees. So day 2, you have 65 rupees. Day 3, 80 rupees. You're actually manually creating a mathematical pattern right there just by maintaining a consistent habit. Which brings us neatly to Section 2, Decoding Arithmetic Progressions. Let's look at the blueprint. Okay, the absolutely crucial thing to grasp is this definition right here. An arithmetic progression, or we'll just call it an AP to keep it simple, is really just a sequence of numbers where every step up or down is identical. You take a term, you add a fixed number to it, and you get the next term. That's the whole shebang. It's basically like an elevator that only ever travels the exact same distance between floors. We call that exact fixed distance the common difference, and we usually denote it by the letter D. Now, D is literally the DNA of the progression. If D is positive, like adding 15 rupees to your bank, the progression grows. If D is negative, like say reducing your screen time by 5 minutes a day, it shrinks. And yes, D can absolutely even be 0, which just gives you a completely flat, constant sequence. And this table right here brilliantly illustrates how we build the progression mathematically. Let's call our very first starting number A. To get the second term, we just take A and add our difference, D. For the third term, we take that new result and add D again, so we get A plus 2D. For the fourth term, it's A plus 3D. Do you notice the pattern there? The number attached to D is always exactly 1 less than the term number you're looking for. Moving right along to Section 3, Finding the nth term. Think of this as your mathematical time machine. Because honestly, what if you need to know the 100th term? You absolutely do not want to sit there manually adding D 99 times. No way. That's exhausting. Instead, we use this elegant little formula, Tn equals A plus n minus 1 times D. Think of Tn as your destination. You get there by taking your starting point, A, and adding your step size, D, multiplied by the total number of steps you need to take. And that number of steps is always your destination number minus 1. Let's actually take this out for a spin using our honeycomb example. Remember, the first ring A had 6 cells. The difference, D, was also 6. So, how many cells are in the 7th ring? We just plug it right in. We want the 7th term, so n is 7. That means Tn equals 6 plus 7 minus 1 times 6. That's 6 plus 6 times 6. 6 plus 36 gives us exactly 42 cells. Boom, instant calculation, no drawing, a giant honeycomb required. All right, let's jump to Section 4, summing it all up. This is the brilliant shortcut. Because sometimes we don't just want to know what the final stop is, we actually want to know the grand total of every single number in our sequence added together. To do this, we need to look at this hidden symmetry inside arithmetic progressions. Look at the sequence 2, 4, 6, 8, 10, 12. If you add the very first term, 2, and the very last term, 12, you get 14. If you step one place inward and add the second term, 4, to the second to last term, 10, you get 14 again. 6 plus 8, also 14.
This perfect built-in symmetry allows us to create an amazing shortcut. And thanks to that beautiful symmetry, we get these two insanely powerful tools to find Sn, which just means the sum of n terms. Now, over on the left is the standard formula. It's absolutely perfect for when you only know your starting point, your common difference, and how many terms there are. But on the right, look at that brilliant shortcut. If you happen to already know the very first term a and the very last term L, you simply add them together, multiply by the number of terms n, and cut it in half. It's literally math working beautifully in our favor to save us time. And now for the grand finale, Section 5, Real-World Math Mastery, tackling those NCERT problems. Look, when you face a word problem, do not panic. I promise you, just follow this simple 3-step playbook. First, read the story and pull out your starting amount. That's your A, and find the constant change. That's your D. Second, just ask yourself, is the question asking for a single value at a specific point in time or a total accumulated amount? That instantly tells you whether to use your TN formula or your SN formula. Finally, step 3, just plug those numbers in and solve. Easy. Let's apply that to this classic NCRT taxi fare problem. The fare is 15 rupees for the first kilometer and 8 rupees for each additional kilometer. Boom, step 1 is done for us. Our starting value, our A, is 15. The fixed amount getting added every single time, our D, is 8. From here, if they ask for the costs of the 20th kilometer, you just grab your TN formula and plug in A equals 15, D equals 8, and N equals 20. Or how about this one? A mason is building a brick staircase. The first step requires 4 bricks, and each subsequent step requires 4 more bricks than the previous one. He needs to build 25 steps. How many total bricks should he order? Well, since we want the total amount, we use our sum formula, Sn. We plug in our first term A as 4, our difference D as 4, and our total number of terms N as 25. Run the math on that, and we find he needs exactly 1,300 bricks. Perfect, precise, and completely manageable. So the ultimate takeaway for today is that arithmetic progressions are not just abstract, boring formulas in a textbook. Not at all. They're the structural blueprint of honeycombs, the foundation of musical harmony, and the logic behind your daily savings. So I want to leave you with this question to chew on. Where else is an arithmetic progression hiding right now in your daily routine? Keep your eyes open, and you might just spot the math literally everywhere. Thanks so much for joining me in this explainer, and I will catch you next time.